My name is Evan Jose, and today I will be discussing my Lab 4 Physics 2020 2212 lab circuits. So the contents are the introduction, part 1 of the experiment, part 2 of the experiment, and the time dependence model, and the results and discussion, as well as a conclusion in the end. To introduce this lab, the purpose is to predict the behavior of circuits containing resistors in series and parallel. Use multimeter to measure the actual values of conventional current and potential differences in the circuits, as well as examine the behavior of ohmic resistors and capacitors. So, the description of this lab is using the principles of energy conservation, or the loop rule, and current conservation, charge conservation, plus definition of steady state. The lab will give a macroscopic view of the DC and RC circuits. So, fundamental principles observed in this lab are the conservation of energy and charge, the loop rule and the node rule, steady state circuits, and Ohm's law and RC circuits. So, a preview of the results is that the values given for the current and voltage given by the online model are the same as the ones predicted from the formulas. So, the system is the circuit, the surroundings are everything else. The model is using an online ideal model. Different combinations of capacitors will be resistors and will be observed. So, the assumptions that we have are resistance of wires is negligible, as well as the resistance of the ammeter is negligible. So, part 1 of the experiment is we have the prediction of I1 equal I2, or the node rule. The experiment is a 1.2, 1.5 volt batteries, 2 ammeters, as well as 2 resistors. The summation of the resistors is equal to 47 plus 100, and I is equal to volts over R. So, 1 ammeter replaced with a voltmeter is equal to 3 volts and 0 amps. And an open circuit has no current, and the potential difference stays constant. So, as you can see from the graphic here, as well as the numbers here, from A to B, that is 3 volts. From B to C is 0 volts, since the straight line. From C to D in the negative direction is negative 0.96. From D to E, it is 0 again. From E to F, it is negative 2.04. And from F to G, it is 0. And from G to H, it is also 0 volts. So, connected ammeter with 100 ohm resistor. The current increased up to 0.06 amps. Less current is in contact with the 100 ohm resistor. Resistance decreases, causing current to increase. And here's a visual model. So, part 2 of the experiment. The experiment now is a 10 omega bulb, 200 ohm bulb, and a 9 volt battery and a 200 mF capacitor. So you have to connect the battery to the 10/2 bulb and capacitor in series, and then disconnect the battery and then time the discharge. And as you can see here is the time-dependent model. As time increases, you can see volts begin to decrease, as well as the natural log of the change in voltage, as well as this linear line here depicting this data. So, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? If this lab were to be done in real life, then the ammeter would have resistance and contribute to a lower current. So, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would your ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So, full charge would be reached immediately since there is no resistor to slow down the current. However, in real life, this would not happen because wires have an innate resistance to the current, and this resistance of the wires would cause the capacitor to charge slower. So, in conclusion, the errors that I observed were precision of ammeter, or that could have happened, or precision of ammeter rounding while calculating, and an error with timing. Improvements that could be made for the next lab could be run more trials and model the experiment with real circuits. Thank you.